Hello everyone, this is Tanisha NAGWANI, a third year student of Integrated MCA course at IIPS TAVV. So in this video, we will see deadlock in operating system, that is the silent system killer. So what is a deadlock? A system frozen in time. Deadlock is a state where two or more processes are permanently blocked, each voting for a resource held by another process in the same set. Here, no forward progress appears, that is, no process can advance without external intervention. And the critical failure mode appears, that is, a fundamental danger in concurrent operating system design. Now we'll see the four necessary conditions of deadlock to appear. The first is mutual exclusion. The second is hold and wait. The third is no preemption. And the fourth is circular wait. So, all these four conditions must hold simultaneously for the deadlock to occur. So, the first is mutual exclusion. Mutual exclusion is at least one resource is held in a non-shareable mode, that is, only one process can use it at a time. The second is hold and wait. In hold and wait, a process holds at least one resource while waiting to acquire additional resources held by others. The third is no preemption. That is, resources cannot be forcibly taken, they must be voluntarily released by the holding progress. And the fourth is circular wait. That is, a closed chain of processes exists where each holds a resource the next process in chain requires. Now we'll see the dining philosopher problem, that is to avoid the deadlock. So the algorithm of dining philosopher says that five philosophers sits around the round table. Each, each needs two chopsticks to eat. One shared chopstick sits between each pair. The deadlock is each philosopher picks up their left chopstick simultaneously. Now all wait independently for the right chopstick held by their neighbor. So the lesson is a perfectly symmetric resource contention leads to a system-wide standstill with no external nudge to break it. So we use the dining philosopher problem to avoid the deadlock. Now we will see the visualizing trap. So that is resource allocation graph. So how the resource allocation graph works is a directed graph where nodes represent processes and resources and edges shows assignment or request. So the assignment edge is a resource to process. The process is concurrently allocated. The request edge is from process to resource. The process is waiting to acquire it, and the cycle is equals to deadlock. In a single instance resources systems, a cycle in the reg, that is resource allocation graph, confirms the deadlock. So in this diagram you can see the state is deadlock. Resources are R1 and R2 and the processes are P1 and P2. Now moving on to the strategies for timing deadlock. So a multi-pronged approach from proactive design to reactivate recovery. So in this we use prevention, avoidance, detection and recovery. So the first is prevention, that is strictly negate one of the four conditions. Example, enforce log ordering to break circular wait. Second is avoidance, that is to use the banker's algorithm to dynamically allocate resources only when the system remains in the safe state. The third is detection. Detection says to allow deadlocks to occur. Then scan the reg, that is resource allocation graph, or wait for graphs to identify cycles. The fourth is recovery. In recovery, it says once detected, abort processes or prevent resources to restore system progress. Now at last we see the prevention, that is making deadlock structurally impossible. So the first is mutual exclusion, hold and wait, no preemption, circular wait, that we have already seen. So to remove these we use we remove mutual exclusion, that is make resources shareable, and then we avoid the hold and wait, that is to request our resources upfront. Then we use allow preemption, that is force resources release if needed, and then we break the circular wait, that is impose resources or drain. These uh, these help us from high prevention effectiveness to low prevention effectiveness, and from the low resource demand to high resource demand. So, thank you.